Good morning, everybody. My name is Ramiro Velázquez. I come from the Universidad Panamericana in Mexico, and I will present you our paper entitled Modeling and Prototype Implementation of an Automatic Guided Vehicle for Smart Factories. Well, this project has been developed within the concept of our mobile robotics group at Universidad Panamericana. Previously, we have tested with walking robots. As you can see, leg robots exploring several technologies like pneumatic, electromagnetic, etc. Wheel robots, several structures such as change, bands, etc. And we have also explored flying robots or drones. Well, the context of this project is industrial robots, in particular material transportation. The objective of this project or this kind of robots is the efficient transportation of materials. The use of this kind of robot has broadened since the beginning of Industry 3.0 and has become essential for the development of Industry 4.0. There are two types of robots for material transportation. The first one is called SDV, or self-driven vehicles. This kind of robots are intelligent robots that are equipped with cameras, lidars, computational vision, and perform autonomous navigations. In contrast, we also have the AGVs, which is automated guided vehicles. These vehicles are less intelligent, if you want to say like that, because they are driven by magnetic tapes on the floor. They are equipped with bar readers and read barcodes, RFIDs, and antennas. Okay, so the most popular AGV known is the one from Kiva Corporation, which is used by Amazon. Amazon has 45,000 units of AGVs across 20 distribution centers worldwide. So it's a very popular AGV out there in the market. Well, our proposal was developed in the context of CONACYT project, which is our Mexican Agency for Science and Technology in cooperation with an automotive industry. And the core ideas we wanted to convey are advanced technology, robust appearance, clear difference with commercially available AGVs, and Mexican identity. After proposing several designs, we arrived to this one. So we chose to get inspired by the Mexican cultures. Here we can see some snakes at the Aztec pyramids, and here you can see also the heads. So for the body, we inspired in a snake. Here you can see the body, and for the head in the jaguar. So these were the inspirations that we obtained to design our AGV. This is the CAD 3D model. Here you can see the resemblance with the previous slide, the jaguar head and the body like a snake. So to implement this prototype, we chose 304 stainless steel, and for the manufacturing methods were laser cut, CNC folding, and TIG welding. So here you can see the structure. This is the model, and this is the implemented. So we can see the resemblance of both. So for the electronic architecture, we had a microcontroller unit, which is equipped with a Wi-Fi model, and there are four main sensors in the AGV. So the first one is a laser to detect the bar tapes, a camera, video RGB camera, a contact switch, a tag reader, and of course this is to convey the motion information. So any operator in the vicinity can stop it with an emergency stop and a motion lamp. The Wi-Fi, we are currently exploring the possibility of having a group of AGVs. Here we can see 1, 2, N, and all these AGVs are connected through a gateway to a central station in order to have this the prototype as a component of smart factories. Here we can see the final prototype. Here we can see the AGV following the barcodes, the motion lamps, the emergency stop, all the electronics, etc. So in the paper we presented two analyses. For the structure, the first one is the structural analysis. The objective of this analysis is to determine the efforts on the structure using finite element analysis to detect potential weak zones. We model two scenarios. The first one is a normal operation, which is the AGV moving, carrying a 700 kilogram load. And the second one is a critical case when the AGV collides with another object. And the most critical situation takes place when the AGV is fully loaded and moving at its maximum speed. So the normal operation is this one. So we can see through the simulations that the maximum effort to be developed is nearly 40 megapascals, as the elastic limit of our material is 200 megapascals. We can see and that there is no harm, there's no deformation of the structure. The maximum deformation is negligible, so very little. But the critical changes a little. So when the AGV collides with another object, we can see efforts up to 355 megapascals. The limit is 200 megapascals of the material. So here we can see that it surpasses the limit. Here on the model, we can see a deformation of almost 4 millimeters. So we can conclude that the structure will exhibit deformation. There will be deformation. So we're going to try to avoid putting key elements such as electronics in this area. We also propose a model, a mathematical model for the prototype. We're not going to get into the details because of the brief presentation, but here, if we could look inside, we can see a differential drive structure. Here you can see two active wheels, two caster wheels, and two other, which the only purpose is to serve as to extend the wagon in order to serve as a loading structure. And we assume all the motions or speeds that could take place in the wheels. Here we can see linear speed, rotational speed, and sliding speed. So at the end, the model give us some parameters. The idea is that upon the input voltages, the voltages in the motors, we can obtain the linear speed in both axes, the angle of rotation, the speed of the wheel, and the angular speed of the wheel. So the model is detailed on the paper. This model can be used to model any sequence that for the AGV. For example, here we can see the voltages to the motors and how the AGV moves. So this model could be useful for modeling or path planning in smart factories. Well, to conclude, we have presented an AGV prototype devoted to transport tools, materials, or finished goods in industrial environments. We were inspired by pre-Hispanic Mexican cultures, which provides a unique identity for our prototype. The AGV's implementation was conducted using advanced manufacturing systems to ensure the precision of all pieces and components. The electronic components are currently being tested to operate in an optimal manner in the context of smart factories. So we are here currently testing all the prototype. Our future work intends to evaluate, to assess the AGV performance within a wireless sensor network. So this is our paper. If you have any questions, please don't hesitate to ask. Thank you very much.